Hi there, we're incredibly honored to have you tuning into our YouTube channel. Today we are looking at KIRCHOFF'S laws and circuit analysis, and we're going to be evaluating a problem that came in Bilingual Grammar School MOLYKO's PREMOCK, and we hope that throughout this video the tips that we're going to be sharing, you can use them to solve the most complex problems that you can ever find on circuit analysis. Make sure that you can leave some comments of love and likes, and you can also recommend what we can solve for the next video. Let's go. So here's the problem. You can just go ahead and pause the video and then just read the problem and attempt solving it first before you check out what we've done. Is that okay? Okay, let's go. So the A part of the problem says define temperature coefficient of resistance stating its SI unit of measurement. Okay, now we're going to go about answering this in a slightly different way. So we're going to recall the very popular data analysis equation where R theta is R0 1 plus alpha delta theta. This is basically the equation that relates how the resistance of a conductor varies with changes in temperature, right? So alpha here is the temperature coefficient of resistance. So if we make alpha the subject, then you realize that, well, we have this equation, this new equation, and clearly you realize that R theta minus R0 is basically a change in the resistance of the material, right? So you have change in resistance of the material divided by the original resistance of the material. This gives you a very fundamental quantity in physics that's called the fractional change of that property. So in this particular case, the property is the resistance of the material. So this is the fractional change of the resistance of the material. So I can easily define temperature coefficient of resistance then as the fractional change in the resistance of a material per unit change in temperature, full stop. And what will be the SI unit? The SI unit will simply be, remember that delta R here and R0 will have the same unit because it's change in resistance, is resistance. And so you'll be left with 1 over delta theta. So the unit here will just be per degree Celsius or per Kelvin. So that's it right there. Let's move on to the next. Alright, so B says state KIRCHOFF'S laws for simple circuits. Well, that's basically the two KIRCHOFF'S laws, the current law and the voltage law. Well, for the current law, you basically have the algebraic sum of currents at any circuit node is 0, okay? And then for the voltage law, of course, in any complete circuit loop, the sum of the EMFs is equivalent to the sum of the potential differences dropped across every circuit load, right? And you go ahead and then you show that the current law is essentially a statement of the conservation of charge. Okay, let's look at the circuit that we already have in this particular problem. Okay, and let's say that we have to apply KIRCHOFF'S current law in this particular circuit. You realize that if I come to the node X, I is getting into that node, and then I2 and I1 are leaving the node, right? So that must mean that I split into I1 and I2. So if I sum up I1 and I2, I should get I, right? That's the meaning of algebraic sum equals 0. So if we get that, that basically means that I is equals to I1 plus I2. But recall that Q is equals to IT. Remember in Form 5? So this means that I is of course Q over T, right? So this means that if I come back to this KIRCHOFF'S current law, I can rewrite it as, in place of I, I'll put Q over T. In place of I1, I'll put Q1 over T. In place of I2, I'll put Q2 over T, right? Basically, the amount of charge per unit time that flows. That's basically what current is. So if where unit time is T, then I is basically a function of the total charge that gets to this particular node, which is Q, and that charge splits into Q1 and Q2, and I2 is basically a measure of how much charge Q2 flows per unit time T, right? That makes sense? Perfect. So if we simplify this equation, we multiply all through by T, you realize that our Q would simply be Q1 plus Q2, which means that the KIRCHOFF'S current law is effectively the law of conservation of charge. We can also do the same for KIRCHOFF'S voltage law to show that it's effectively the law of conservation of energy. That can be your little assignment. How about you go ahead and try that, and you can leave the comment in the comment section below if you've been able to prove it, right? Great. All right, so the reading of the ammeter A, B, and C, the PD between X and Y. All right, now this is where the real work is, right? Now this is our circuit. let's go ahead and evaluate. Remember that there are two laws you have to always apply to every circuit that you see. Law 1 is Kirchhoff's current law. So get to a particular node, look at all the currents that are entering and look at all the currents that are leaving. Now remember that in this particular problem, they did not give you the directions of these currents. So if they just gave you the circuit without the directions, like in this particular case, it's up to you to come up with directions of the part of current. So how would you come up with the directions of the current? Now this is an EMF source here. This is a 12-volt EMF source. What do batteries do? They supply currents, right? Perfect. So this is 12 volts, this is 2 volts, this is 3 volts. Now obviously my assumption here is the greatest EMF source here would be the one to drive current throughout this circuit, and that's what I've basically done. So this guy would drive I, and then the I will come and split into I1 and I2. So this is my decision. You can choose that maybe this 3 volt would distribute current to the circuit, but that's not very practical, and in this particular case it will not be true. So because this 3 volt of course cannot drive current through the 12 volt EMF source, unless this guy has a way greater internal resistance such that the terminal PD becomes way smaller than the EMF that you're seeing here. Does that make sense? So yeah, you can always choose your directions for the current. So in this particular case I've chosen like this, but if you choose your direction from here, you realize that your I2 will rather flow opposite to this my direction, and then your I1 will flow the same, but your I would flow opposite to this my direction. So your current values will be negative. That means that whenever you solve a Kirchhoff's current Kirchhoff's maybe loop problem and your current values are negative, it really means that, well, you have reversed the direction of that particular current, right? So the current basically flows in the opposite direction as indicated in your particular diagram. It's okay, but there's no worries with that one. Let's go ahead and solve the problem. So we'll start with the Kirchhoff's current law, and how do we apply it? Well, of course, this is our I split into I1 and I2, so I is equals to I1 plus I2. Now let's apply Kirchhoff's voltage law on loop 1. Now, hey, this is very important. Remember that when we were stating Kirchhoff's voltage law, we talked about loops, right? That in any closed loop path, the sum of EMFs equals to the sum of PDs. This is loop 1, this is loop 2, because this is like a closed current path. Can you see that? I can traverse throughout this path without lifting my hand. That's a closed loop path. So you realize that I can call this loop 1, I can call this loop 2, and then I'll traverse in this direction, because then the direction that you're traversing in is very important. That's why you see me indicating these arrows. Here I'm traversing clockwise, and then here I'm traversing anti-clockwise. It's okay, you can always do that. So you have to stay dynamic and very flexible when you're dealing with Kirchhoff's laws. So some students think that you must always go clockwise. No, that's not true. Again, remember that these things are dealing with the conservation of charge and the conservation of energy, and these things are always true regardless of who you are, what race you come from, or what direction you want to go. Okay, let's apply Kirchhoff's voltage law on loop 1. So we'll start with summing all the EMFs in loop 1. Watch what is happening here. Watch very carefully how I got this equation. Now if I traverse in this direction of this car, like what I've indicated here, so this is how I'm going clockwise. So if I go like this, I'm moving from the negative to the positive terminal. The longer terminal is a positive terminal, so this means that this EMF source is positive. Okay, so I have 12 volts there. If I traverse and I come down like this is an EMF source. I will move from the positive terminal to the negative. That means that this EMF here is negative, so I have -2 there. So I have 12 minus 2 already. Now let's sum up all the that's some of the EMFs. We're done with the EMFs. Now let's sum up all the PDs. Now if I'm traversing like this is 2 ohm here. This is the internal resistance of this particular battery. So if I traverse like this, remember that I'm traversing the direction of this current I. Can you see that? I'm traversing the direction of this current I. So the PD will be positive. So I have 2 times I, because this is the current that this guy distributes I. This is the I here. So I have 2 times I, and then I have 8 times the I. So I have 2I plus 8I. And then again, I'll traverse down like this because this is the closed loop part I'm traversing on. So this is my I1 now. I1 times 8. So I have 8I1. And then if I come down here, this guy has an internal resistance, so I1 flows through it, so I have 2I12 there. Can you see that? Another way to solve it is just to recognize that this 8 ohm and this 2 ohm are in series, and then you sum them up, so it just gives you 10 multiplied by this I. You simply get 10I, and then you can sum this 8 and this 2 since they're in series, and then you always have 10 10 there. Okay, you can always do that. Okay, so that when that simplifies easily to this. So if I simplify this further by dividing all through by 10, you realize that I plus I1 equals 1, and that's my equation 2. Make sense? Perfect. So applying Kirchhoff's voltage law to loop 2, then you realize that we'll basically do the same thing, but I'm traversing the opposite direction. So EMF will be, this is positive, come down this way, this will be negative because I'm moving positive to negative. Can you see that? And then of course the PDs. Now look at this. This is 5 ohm, this is 10 ohm. The two of them are in series, so I'll just sum them up. That gives me 15. But I'm traversing like this, opposite to this current value. So this PD must be negative because the current is traveling opposite to my direction of traverse. So I have negative 15 I2 there, like that. And then my 10. So if I traverse and I come down, I'll be traversing in the direction of this I1. So that's 8 plus 2. That's 10. 10 times I1. That gives me 10 I1. Perfect. So we have all of that. It's really important at the advanced level, this is the note that I've put here, that you recognize that whenever you get the two equations that you get from Kirchhoff's voltage law, equation 2 and equation 3 in this particular case, there's always going to be one current value that is consistent for both of these two equations. Don't touch that current value. Watch this. This is I1 here. This is also I1 here. Don't touch that. You can touch I, you can touch I2. If you dare touch I1, you are going to go in loops and loops and loops in trying to, solve the problem. So what we're going to do is we're going to use equation 1, which already says I is equals to I1 plus I2, and then we're simply going to put this equation 1 into equation 2. So in place of I, we're going to put I1 plus I2. Okay, we're touching the I. So let's go over here and do that. So put 1 in 2, we're going to have then that, of course, we'll now have 2I1 plus I2 equals 1. So that gives us now equation 4. Now if you realize this equation 4 and this equation 3 have the same parameters, I1, I2, I1, I2. So what do we need to do? Now this our equation 4 is 2I1 plus I2. This equation 3, you have 10I1 and then 15I. So the initials are not, the coefficients are not corresponding. So what do I do? If I divide this equation 3 by 5, watch this. If I divide this guy by 5, I'll have 2 here, which will correspond to this 2 here. So that's what I have to do. So 4 minus equation 3 divided by 5. That's what I've just done here. You understand that? So this is my equation 4. This is my equation 3 now divided by 5. So because 10 divided by 5 gives me 2. 15 divided by 5 gives me 3. 1 divided by 5 gives me 0.2. Yes, you can do that. If I subtract that, the 2, I'll have this guy disappearing, and then I'll have 4I2 here, and then I'll have 0.8 here. So my I2 is basically 0.2 amperes. Very easy, right? So you take this 0.2 amperes and then you put in any one of the equations, and then you get the other values of I, 0.6 and 0.4 amperes. So what does this mean? It means that my meter A, this meter A would read I1. Would read I. Can you see that? Because this guy supplies I, and then there's the I that will enter back. So this guy A would read this I. So A reads 0.6 amperes, which is I. And then B, look at B. B would read I1. So what is our I1? I1 is 0.4 amperes. And then C would read I2. So I2 is 0.2 amperes, and so on and so forth. So let's go. This guy says the PD between X and Y. So how do we get the PD between X and Y? Okay, there are so many ways to do about this. Remember that, hey, the electric field is an example of a conservative field. What is a conservative field? It's any field that the work done in moving a particle between one point to another is independent of the path taken. Okay, so to move a charge from X to Y, I can go directly from X to Y like this, or I can go like this all the way to Y like this, or I can move from X and then all the way to Y like this. So to show that the electric field is an example of a conservative field, I'll solve this in 2 ways. Okay, so method 1 would be me moving from X directly to Y. Okay, let's look at it. So we'll first of all recall our current values, and then we'll go ahead. Method 1, we're going to move from X directly to Y. So how do we move? Now the potential at X is called Vx. Okay, that's the electric potential at X, because again, remember that charge is only able to move between 2 points if there's a potential difference between those 2 points. So if between X and Y there's no potential difference, then I1 will be 0. It's as simple as that. So there will be no current flowing through this path. So B would reach 0 amperes if there's no electric potential difference between X and Y. Is that clear? So because I1 is not 0, that means that X and Y exist at 2 different potentials. Now, for us to move like that from x all the way to y, then we have to say, okay, what is the potential at x? So let's arbitrarily call it Vx. Now, what is, as we traverse from x all the way to y, remember that there are loads here, and these loads have their different potentials that are dropped across them. Does that make sense? So across this 8 ohm resistor, what potential is dropped across it? Of course, it's 8 multiplied by I. That's voltage, right? Current multiplied by resistance. If you remember Ohm's law. So you realize that 8 times I1 is the PD drop across this guy. But now watch out. When I'm adding the PDs and the EMFs on one side, then the PD becomes negative if I'm traversing the direction of the current. Okay, so watch this. This is Vx. Okay, I've written it down. Now if I go like that, I1, I'm traversing the direction of this I1 across 8 ohms to get to X, to get to Y. So you realize that that PD will be negative. Okay, and then if I go across again, look at this 2 ohm. I'm traversing the direction of the current that is going through it, negative PD. And then if I go this, if I move across this voltage source, it's positive to negative, so this voltage becomes negative, right? Because again, of course, by convention, whenever I move from positive to negative, the EMF is negative. And then if I go all the way at the end, that basically gives me the potential at Y. That makes sense? Great. So if we simplify this, we have Vx minus Vy, and then we send every other thing the other way. And so you realize that our Vxy, because Vx minus Vy is simply Vxy, is 4 plus 2. Why do I say 4? Because I1, remember that I1 is 0.4. So 0.4 times 10 gives me 4. Plus this 2 gives me 6 volts. So Vxy is 6 volts. So that's a PD between X and Y. Now, what does this mean? Because it's positive, clearly the potential at X is greater than the potential at Y. So X is at a higher potential, okay? So the current will flow from X like this all the way to Y. There are a lot of ways, and this is really important in paper 1 for you to fully understand. So method 2, what are we doing? We are simply saying that, all right, instead of traversing directly like this, let's traverse in the opposite direction like that, okay? So let's go Vx, and then we are going. So since we're traversing the direction of the current, this PD here will be negative. So 10I2. So we have negative 10I2, and then we go like that. The resistance here is 5 ohm. Again, we're traversing the direction of current, so that PD is negative, negative 5I2. And then again, look at, we move from positive to negative. So this EMF here is negative, negative 3. And then once we are done with these loads, we go all the way to Y. So that gives us the potential at Y. So you realize that if we simplify this, Vx minus Vy, so basically, you know, send things one way, send the others the other way. And so you realize that Vxy becomes what? 15I2. Remember that I2 is 0.2. When you multiply those two, you simply have 3. And then plus this 3, that gives you 6 volts, exactly the same as what you did over here, telling you that what, regardless of the path that you choose to go through, the PD between X and Y is exactly the same. Again, reinforcing the fact that the electric field is an example of a conservative field, just like gravitational field and magnetic field. They are all conservative fields, okay? So hence X is at a higher electric potential because again Vxy is positive.
Please don't forget to like, comment, share, and videos and